In this video, we're going to continue our discussion of the effect of concentration on free energy changes. So we know that for processes occurring under non-standard conditions, we can calculate the free energy change using the following equation. And in this equation, we take into account the concentrations in the form of our reaction quotient Q, where Q is equal to the concentration of our products divided by the concentration of our reactants raised to our stoichiometric coefficients. So what effect do the initial concentrations of reactants and products have on the free energy change of a reaction? To answer this question, let's look at two possible scenarios. The first possible scenario, we start our reaction off with a mixture containing a small amount of reactants and a relatively large concentration of product. Under these conditions, how is delta G going to change relative to delta G standard? Well, under these conditions of a small reactant concentration, large product concentration, delta G will be less negative or more positive. So delta G will be larger, relative to delta G standard. Put another way, the forward reaction is less likely to be spontaneous and the reverse reaction is more likely to be spontaneous under these initial conditions. Our second scenario would be if we had an initial concentration of reactant that's relatively high and an initial concentration of product that's relatively low. Under these conditions, how will delta G change relative to delta G standard? Well, under these conditions, delta G will be smaller relative to delta G standard. In other words, it will be more negative, less positive. So if delta G standard is negative, delta G will be more negative. If delta G standard is positive, delta G will be less positive compared to delta G standard. Put another way, the forward reaction under these conditions is more likely to be spontaneous. So let's look back and talk about these two scenarios in more detail. The first scenario, we have a small concentration of A, initially a large concentration of B. We said that the reaction is less likely to be spontaneous. Let's explain why that is. To explain why that is, let's look at our equation that allows us to calculate delta G. And let's start off by calculating Q, or looking at Q. If we have a large concentration of B, a small concentration of A initially, how is that going to affect Q? Well, Q should be relatively large, right? Q will certainly be greater than 1. What if we take the natural log of a number that is greater than 1? Well, you can play around with that in your calculator, but you'll see that any number that's greater than 1, if you take the natural log, it will always be positive. So under these conditions, large B, small a, our natural log of Q will always be positive. Now, if we multiply that times RT, of course, these values are positive. We'll end up with a positive value overall. So essentially, we're going to add some positive number to delta G standard. Well, if we add some positive number to delta G standard, that will give us a delta G that is bigger than delta G standard, more positive. So we can say this. Under these conditions of high reactant concentration, or high product, low reactant concentration, delta G may or may not be positive. We can't say because we don't know the sign of delta G standard. But delta G is more likely to be positive. Okay, so the bigger this concentration of B and smaller concentration of A, the more likely delta G is to be positive. And of course, that would give us a reaction that is less likely to be spontaneous. So the more likely this is to be positive, the less likely the reaction is to be spontaneous. So again, be sure you appreciate this mathematically, why this reaction under these conditions is less likely to be spontaneous. Let's look at our second possibility, where we start off with a relative high concentration of reactant and a relatively small concentration of product. We said this reaction, under these conditions, the reaction is more likely to be spontaneous. Let's explain why that is. So under these conditions, we have a relatively high concentration of reactant, relatively small concentration of product. How is that going to affect Q? Well, if we divide a small number by a large number, Q will be small. It will be less than 1. Well, what if we take the natural log of a number that's less than 1? Well, that number will be negative. Again, you can check that in your calculator. Punch in some numbers, 0.1, 0.01, 0.001. You'll see all of these, if you take the natural log, will give you a negative value. Well, if we multiply that negative number times RT, we'll end up with a negative number. So essentially, under these conditions, this term over here, RT natural log of Q, will always be negative. So we're going to be subtracting some number from delta G. So that tells us that delta G is going to be less than delta G standard because we're always going to be subtracting some number from it. So if we're subtracting some number, that means that delta G will be less positive or more negative than delta G standard. So delta G may or may not be positive, but we can say this. We can see that delta G is more likely to be negative when we have a large reactant concentration, small product concentration. And of course, if we have delta G is more likely to be negative, then the reaction is more likely to be spontaneous. So let's take a look at a problem, kind of some made up numbers here, to help us illustrate that. In this hypothetical reaction, we're given delta G standard of positive 6 kilojoules per mole at a temperature of 25 Celsius. Calculate delta G if the initial concentration of A is 10 molar and the concentration of B is 1 molar. Okay, calculate delta G there. Then, what if we increase the concentration of A to 20 molar and decrease the concentration of B to 0.1? How is that going to affect delta G? First of all, pause the video and predict what you think might happen to this value here. Will delta G begin to go up or down relative to this number? And then plug those numbers in and calculate to see what you get. Pause the video and give it a try. Okay. So let's start off first with our prediction. Here, we're increasing the concentration of A and decreasing the concentration of B. Again, at standard conditions, everything would be 1 molar. So A is higher than it would be under standard conditions. So I would predict that the reaction is more likely to be spontaneous. So delta G should be less than this delta G standard under these conditions. If we plug our values in and calculate delta G, here's my delta G standard, RT in Kelvin, and again we're dividing product by reactant, we get a delta G of 0.3 kilojoules per mole. So you can see if we increase the reactant concentration relative to the product concentration, delta G will decrease, become less positive relative to delta G standard. So we're becoming more likely, it's beginning to get more likely to be spontaneous. Even though here we're still non-spontaneous. We're closer to equilibrium. So let's take a look at part B. What if we increase the concentration of A even bigger and decrease the concentration of B even smaller? I would expect delta G to get even smaller relative to delta G standard. In fact, it's probably going to be negative in this instance. So let's plug in our values here. Again, we have our delta G standard, RT, and we're calculating Q. And here we get a delta G of negative 7 kilojoules per mole. So as we continue to increase A and decrease B, our reaction is getting more and more likely to be spontaneous until eventually it becomes spontaneous under these new conditions. So be sure you have a good grasp on the relationship between concentration and delta G, concentration and spontaneity. Be sure you can discuss it and calculate it.